quando hai finito cominciamo, eh?
Ma io sono quello dopo in realtà.
Sì, sì, ma così...
Grazie.
Quello che mancava. Enrico. No, ma in realtà questa qui credo che sia Antonella. Sì, cioè è tua, vero? Sì. Quindi la sì, però la volevo dare
la mettiamo, quella di Enrico la mettiamo dopo.
Vicino al coccodrillo. Che mi fa vedere dove sta male.
People are still coming, we wait another few minutes so that they won't miss your talk. Un po' meglio, c'è ancora la cosa di spegnere?
No, è quella della lavagna.
No, la lavagna la spegniamo, ma queste qui non si possono spegnere più?
Sì. Se fate troppo buio poi a noi le facce vengono tutte nere.
Va bene.
Cioè così
allora
no,
meglio che
no,
Giancarlo, forse questa fila sì, quella
così.
no.
Così, sì, va bene.
Grazie.
Okay, so I think we are wait a minute, we are going to start this afternoon session.
The microphone. Anna, it's better that you take the gelato.
Sì. Ma io ho una voce che non mi serve.
Yes, I know, ma nella videoconferenza non c'è.
Va bene, la videoconferenza. Allora, so we start this first afternoon session. I am here to take care of it. And sì, lo devo accendere.
No, è acceso.
No. Sì, adesso è acceso. So, speakers will have 25 minutes each. And we will use 20 for the presentation and 5 for discussion. And so I will warn everybody after 15 minutes, once you have 5 minutes left to complete your talk. So we start with Murray Holland. He will tell us about continuous real-time tracking of the quantum phase below the standard quantum limit. And this is, of course, the quantum part of the conference. Please.
Okay, let me begin by just thanking Marilu and the other organizers and so on for having me here. It's a wonderful place to come, even though it's a little hot. Far caldo, no? So my name is Murray Holland and I'm from Boulder in Colorado, from Jilla. I work with Junyi, who gave the first talk today, and others there, experimentalists and theorists on a number of different aspects of developing theory of quantum systems in this kind of second generation of quantum mechanics, with this sort of idea that you can take quantum mechanics and not just understand physical system that nature gives us, but actually try to build and engineer quantum systems that do things for us using the rules of quantum mechanics. And I think we're at a spectacular age where that's really something that is playing a huge role in pushing the forefront of physics in general. So I'm going to tell you about what is really a technical presentation, but I've tried to make it a little bit understandable from the point of view of why we are trying to do this. Yeah, so it's a story of two competing superradiance processes, and I want to just emphasize that a lot of the work was done by a PhD student in my group, Athreya Shankar, who some of you know here, experimentalists in the group of James Thompson, And so these three people here are really thinking about doing this, okay? And Ithrea and myself are the two theorists on this collaboration. So why are we doing this? Of course, clocks are really the thing that we use to measure time. A lot of the importance of clocks goes way back to things like navigation around the Earth, where you had to use clocks in ships to measure longitude. This is a picture of Huygens' clock from more than 300 years ago, 350 years ago. And these kind of pendulum clocks, this is a picture that Jun showed, is kind of the idea that we have about sort of forming a ruler of time. Tick marks of time, they're associated with something oscillating back and forward. So a classical mechanical oscillator like this, what do you need to do to make a good clock? Well, you try to make a high Q pendulum that will just oscillate many, many times before it decays. And then you have to have a counter that just counts how many times it goes back and forward. And it's this counter that I'm going to talk about today. It's to do with the phase of the oscillation that measures time. So we don't have these kinds of clocks. We have these kinds of clocks, but they're really exactly the same. If you have a quantum system that's a superposition of a s orbital and a p orbital, and you put it in a 50-50 superposition of these two possible states, because they have different energies, sometimes they destructively interfere on one side, and sometimes they destructively interfere on the other side. So you can really think of an atomic clock as an electron probability density that is just oscillating back and forward on the atom, much like a pendulum swinging back and forward. So the atomic clock and this pendulum clock are really the exact same thing. But the rules of quantum mechanics come into play. First of all, you have things like superposition in quantum mechanics. You have things like the fact that you can start this thing oscillating, but the amplitude cannot just slowly decay like it does in a mechanical system. It has to spit out a photon. It has to have a quantum jump. So fundamentally different ways that dissipation enter. And not only that, but our oscillators are really high Q. Their optical frequencies may be 10 to the 14, 10 to the 15 hertz, and they can sit there oscillating for an hour without decaying. So that's a Q of like 10 to the 17, something in that order. So these are amazingly high Q clocks, okay? And that's basically where atomic AMO physics is coming to this conference from, because with this incredibly high precision metrology capability, you can then start to explore the sort of boundaries of physics, fundamental physics and so on. So that's the basic idea. There are actually two kinds of clocks that we have in AMO, and they're the two complementary things. And this slide that I'm going to put up now, I think could be around in 50 years' time. Okay, this is the sort of full gambit of possibilities. This is the little cavity that Jun showed you. This is one way of making a ruler of time. It's an empty cavity. It's made out of pure silicon. There's a little picture here of the silicon lattice. A single silicon crystal. This is what Jun uses for his high-quality laser, with coatings on these two sides of the cavity. And you've got to count the number of wavelengths that fit in here, but that defines a very accurate distance. And with the speed of light, it defines a very accurate frequency and therefore time. So this is the kind of best laser. This is the one that has the coherence length that's a good fraction of the Earth to the sun. Another way of doing it actually is to use the high quality oscillators that come from nature. And this is an artist's rendition of the matter version. This is a light version, but there's a kind of matter version as well, where you could use these very narrow line width transitions in atoms and use the actual high Q nature of that transition to make the clock itself. And in that case, you could have fuzzy walls like this. And this is a picture of super radiant light coming out. And this is another project that we're working on in Jilla, a little bit like an active laser that can also be used for a frequency, for a time standard. So basically you come to the table with this kind of clock. And the problem is to make a quantum measurement of the clock that allows you to extract the time. That's what I'm going to talk about today. So the key thing here is the word phase. If you think about just a mechanical pendulum, you can sort of start your time when it goes through the origin, and then you've got to look at it oscillate, and you've got to measure what phase it is at each point in time later. And you know that measuring phase in quantum mechanics is a very subtle question, and that's basically where you start to have to think about what happens in terms of quantum measurements and quantum measurement theory when you start to explore this kind of phase measurement. So what do I mean by this? Here is the simplest possible thing that I think I could put on the board. This is a two-state quantum system, spin 1/2 system where something could be spin down or spin up. And the idea is that you've got to try to measure a phase of an oscillation, something like the phi of t that's sitting in the superposition. So we can't do that directly. We can measure on our particle whether it's spin down or spin up. But it's more difficult to extract what is the phase of the superposition between these two states. That's not a direct observable in quantum mechanics. And so this causes a lot of difficulty. What we typically try to do is to visualize this by representing these complex numbers on the surface of a sphere. So a spin 1/2 system can be represented on the block sphere, basically spin down being the south pole and spin up being the north pole, and this phase representing the azimuthal phase around the z-axis. And if you've got n of these spins, you can think of them as n little arrows which you put tip to tail, and you just get a larger sphere of radius n divided by 2. And so that's what I've drawn for you here. And the idea in these atomic clock experiments is to try to extract this processing phase, which is the pendulum oscillating between these two states, as it goes around the z-axis. So it's a quantum measurement problem. And there's some subtlety to that. As I said before, you cannot measure that phase directly. You can measure populations. You can find how many atoms are spin up, that's like projecting on the z-axis, or spin down. You can actually measure along any axis you like, but you can't measure phi directly. So this is actually not a trivial problem to solve. It's a really fundamental problem. You cannot construct in quantum mechanics a true phase operator. And there are many, many papers on this. People have their own views about this point of view, this problem. It's got a long history in quantum metrology. And phase and number kind of form a conjugate pair. In particular, when the number is very large and the phase fluctuations are very small, you can write a delta n, delta phi uncertainty relation. But it's not a true conjugate pair. And you can sort of see that by the fact that if you, for example, if you take a state that has a well-defined number, the phase can only ever be uncertain to avoid a 2 pi because it's got a restricted domain. Okay, so it can never be a truly uncertain quantity in the sense of position and momentum. So because of that, you can do a lot of things. You can define things like phase localized states. If you have a bound on how many particles you can have in your quantum system, you can construct things that look like well-phased localized states. You can define things operationally and ... There's a long history here. One useful concept is the idea of a spin coherent state, which means that if I take a lot of these arrows and I put them tip to tail, there's a little bit of quantum noise in each one associated with the quantum mechanics, and that generates a little fuzzy blob for the tip of this vector. And that little fuzzy blob is a circle, and it's called a spin coherent state. And it has a sort of uncertainty in phase and uncertainty in number that people refer to as the standard quantum limit. And it's just what happens if you get a whole lot of independent particles and you put them together. So how do we measure phase in these AMO experiments? And there is only there's an almost ubiquitous answer to this for almost every experiment that exists. Almost everyone tries to measure things like the frequency of your atomic clock using a specific method. And this is the Ramsey fringe method, which has had an enormous impact in atomic physics. And it's very simple to think about. The idea is that you could have a lot of atoms and you could prepare them in one state, and I've labeled that state spin down here. And then you could rotate those atoms by applying a field that causes them to rotate about one of these axes, for example, the y-axis, and bring those atoms all up to a superposition of being spin up and spin down, which lies on the equator. And then you could go away and let them freely oscillate and freely evolve in the field. And that's the phase that you're trying to measure. And to measure this phase, you can't measure phase directly, but you could do a second rotation, and here's the second rotation, and then project onto the z-axis to measure the populations. And that's basically what everyone does, this method of separated oscillatory field. There's a Nobel Prize for this. I would say it's the workhorse phase measurement device in AMO. And what you see then, if you measure the population, which is the expectation value of sigma z, it's the number of spin-up atoms compared to spin-down atoms, is that if I change the frequency at which this processes by changing a detuning, what I'll see is fringes. I'll see maxima and minima that go between +1 and -1. And when Jun measures the frequency of his clock, this is exactly what he does. Okay, so this is Ramsey fringes. But there are some problems with this. First of all, you can only measure the frequency to a sort of precision that's allowed by the rules of quantum mechanics. So the idea is that you sit here somewhere on some fringe where there's a large gradient. You go out as long as you possibly can by having many, many cycles. And then you've got like n atoms to measure, and each one you're going to decide to throw a coin. Is it going to be up or down? And so there's a kind of a projection noise, a binomial projection noise associated with your flipping of the coin. And that's quantum mechanics for you. It comes in automatically. It's the noise in quantum mechanics, and it gives you a fundamental limit to the precision with which you can measure frequency using methods like this. Now the question is, can you do better? And the answer is quantum mechanics allows you to do better. This is assuming you have a whole lot of independent little quantum systems, a whole lot of independent spin 1/2 systems, and you can do better than that by using entanglement or correlations in quantum mechanics. And so one of the things that we're working on is trying to work out better ways of measuring the phase in quantum mechanics using the fundamental limits that quantum mechanics provides for us. Okay, so here is my phase that I'm trying to measure. And the phase accumulates as the time integral of some frequency. So d phi dt is some frequency that I'm trying to measure, just like I showed on the previous slide. This is the paradigm of Ramsey, and written as a block diagram, just what I showed you on the previous slide, but just written as a sort of a symbolic way. What you have to do is prepare the state of your quantum system, just sit there, let it evolve, and then form a rotation so that you can then project it so that you measure a population, and then make that population readout and back out what the phase evolution has been. And if you want to study something that's evolving in time, you have to do the whole thing again. You have to come back, you have to re-prepare, and you have to re-measure the phase. And clock experiments do this all the time. There's a long wait time while the system is being prepared. The atoms are being cooled, they're being trapped, and so on. So you have to do this repetitively. So this is Ramsey fringes, rotations to measure populations, state preparation, reinitializing for each measurement, and then a fundamental square root of n that comes from the tossing of the coin when you do this projection. So I'm going to tell you here about another possibility that uses the rules of quantum mechanics to improve the ability to measure phase in many systems. And it allows you to continuously read out the phase in one of these kinds of AMO clock experiments. So the idea is we want something to come out that's proportional to the phase. This thing here, IFT, is a current, okay? It comes out of a detector called a photocurrent. The idea is that we're going to prepare the state and we're going to let phi evolve and we're going to sit there measuring the photocurrent and always be able to tell what the phase of my clock is as it accumulates with time. There's no rotations to measure. There's no reset for repeated measurements. It's a totally different paradigm for measuring phase in AMO physics. And in fact, unlike the square root of n, you can do much better using quantum correlations. You can go below the standard quantum limit. And in this experiment that we're thinking about, sort of 11 to 12 dB is the sort of number that I would give. And each 3 dB is a factor of 2 in the variance, okay? So you can get much better than you can. It means that you need to use fewer atoms, or if you have a certain number of atoms, you can do better. So how does this work? Well, here is the scheme. The idea is that I have atoms in an optical cavity, and what I do is I shine light on them and they scatter that light into the optical cavity mode that bounces back and forward between these mirrors. I have two red and blue arrows here. So there are two processes which can do the scattering. And the idea is that I'm going to set things up so that they destructively interfere and that no light gets into the cavity. And if I tweak the phase a little bit that I'm trying to measure, that destructive interference isn't going to be perfect. And if that destructive interference isn't going to be perfect, I'm going to look at the output light using the homodyne detection, which is a common method in AMO, and I'm going to measure a difference current between two detectors, and it's going to wiggle up and down, and that photocurrent is going to be a direct measure of my phase, and I can monitor that continuously and in real time. Okay. So these two processes are called Raman processes. I'm going to shine light on here, and they're going to go into the cavity mode. So the red arrow here corresponds to absorbing a photon and emitting a photon into the cavity, and the blue corresponds to the reverse, absorbing this photon and emitting this photon into the cavity. And you can sort of see that there are two processes going here which produce photons in the cavity, and quantum mechanics tells me that they could constructively or destructively interfere. So I want to set things up so that it works right. I know this is a complicated internal structure, but it's really just a two-level system because we're so far detuned from the excited state that I'm going to remove this excited state from the dynamics altogether using adiabatic elimination. And these two colors of light are offset from the cavity frequency, which sits here at omega c, by the same amount. And that same amount corresponds to the energy difference between the spin-up and spin-down states. So this process causes destructive interference. So let me sort of show you a little bit about why that works. Here is the situation when the phase is 0. If the phase is 0 of the atomic system, it means that we're in the Jx eigenstate. It means that we have equal amounts of the J plus raising operator and the J minus lowering operator. And if you're perfectly on resonance, the cavity field that you produce is always 90 degrees offset. It's like if you drive a mass on a spring with low frequency, it drives in phase, a high frequency out of phase. And if you're exactly on resonant, it drives at 90 degrees out of phase. That's exactly what we see here. So the J plus produces this blue arrow, and the J minus produces this red arrow. And these two arrows point opposite to each other, and you get no electric field in the cavity and no photons produced. If you have a little phase shift of the atomic ensemble, you get a little shift here between J plus and J minus, and these arrows no longer oppose each other, and you get a little bit of field, and you can see that in the field that comes out of the cavity. So measuring the field out of the cavity tells you what the atomic phase is doing, and this is the heart of what I'm talking about. You get a kind of QND measurement of this JX, and I'm going to show you what I mean by that. So mathematically, this process is very, very easy to write down. It's straightforward, simple quantum mechanics. Here are the two processes that I just described. You can produce a photon with either going from this state to this state or from this state to this state. And you can do the Hermitian conjugate having the opposite processes. And then I can go through just some operator algebra and rewrite this in terms of the x quadrature of the light, which is A plus A dagger, and the Jx operator of the atom. And this is a famous kind of Hamiltonian called a QND Hamiltonian. It allows you to make quantum measurements on a system without having any back action on the system. The idea is that if I want to measure Jx, what I need to do is to measure an observable which is conjugate to this first one. So if I measure the y quadrature of the field, I can get a QND measurement of the x component of the atom. So it's like replacing the complicated Ramsey sequence with something that measures in real time. This is called a Jaynes-Cummings or an anti-Jaynes-Cummings interaction. So I'm just going to show you a little bit about a thought experiment here. Imagine that we've got a signal that looks like this, and I stick in there some time window over which I try to say, what is the phase of my quantum system when I measure the output current for that time? So the idea is that I take my output average current, I make the measurement of the field coming out of the cavity, and as I said, I have to measure the Y component. It's a certain measurement of my homodyne detector. I use my rules of quantum mechanics to estimate what the phase is of my atomic system, and from that I can extract the phi of t in a continuous way. So this kind of replaces this whole paradigm of Ramsey fringes with a continuous phase measurement. And how long should I set this measurement time? Well, at least long enough to measure Jx at this level of the projection noise. And this is just an example of doing this. Here I am looking at an atomic system for a long time. As I accumulate information, I acquire information about the phase, and it puts it into a state. And Jun mentioned this actually. This is called a spin-squeezed state. It uses entanglement between different atoms to arrange it so that the phase between all the atoms is extremely well correlated, better than you would have for independent particles or standard quantum limit. And we've just imposed on this a little sinusoidal perturbation of the energy of the levels. And you can see that by tracking the output photon field, we're able to reconstruct that imposed sinusoidal phase pattern by using the rules that I just specified. And we don't even just do it at the standard quantum limit. Not only is it non-destructive, not only is it real time, but because of this spin squeezing, we can do it better than you can do by any classical system. So we think this is going to be interesting. This collaboration is now sort of involved in taking these rules of the game and trying to work out how you can apply this to real AMO experiments. And I think it'll be important for sort of the future atomic clocks. So I'm going to finish there. Let's just leave this. There are a lot of future directions, things to think about in actually really doing this. I didn't discuss a lot of the real world imperfections, things like scattering of photons, things like shifts of the levels due to the drive lasers and so on. But honestly, we think that none of these are real showstoppers. And I think this will be an interesting experiment to do in the future. So with that, I'll stop. Thank you for your attention.
Question? We have 5 minutes for question on this interesting and apparently simple talk. Just apparently.
Mm-hmm.
Please.
Thank you, Murray. Just a question about quantum non-demolition measurements. Now, I'm sure that what you said is right. I'm just wondering, is it possible to construct an experiment whereby once you've measured your phase with this non-destructive method, you could then, via interference with another identical quantum system, infer information about the spin-up or spin-down parts, and that would then contradict your sort of non-back action? I mean, is that completely loophole-proof?
Could you explain what you mean about like another quantum system? Do you mean an identical experiment?
Yeah, an identical, and then make them interfere, and hence predict the outcome of that experiment, although you wouldn't be able to on basic grounds. So that wouldn't contradict what you said about no back action on the system.
So I think implicit in all of this, this idea of sort of measuring with homodyne and heterodyne measurements is this idea of a local oscillator that's somehow sitting back in the background as a time reference, and that could be another quantum system. And so what you'll end up measuring if you do that, when you look at two quantum systems, you'll end up measuring the relative phase between them, and that's all you can ever do in quantum mechanics. You know,
right.
That's what you're given, right? That's the only thing you can measure is a relative phase between two things. So
that means there's no contradiction.
It comes
there.
back to what Jen was saying earlier about what is time, okay? Mm-hmm. And this is really defining, like, what is the best precision that you can ever make a ruler of time? What tick marks can you actually resolve, you know? And this is the idea that you could use quantum mechanics to generate a quantum advantage, right? Something that goes beyond anything that you could do with a classical system and end up with a more precise phase reference.
Okay, thank you.
Any other question? Please.
Well, I think they could probably hear me.
No, they want you to have the microphone.
Well, hang on.
That's the rule.
Okay. So if I remember, the original reason that they started using Ramsey was because you have these atoms propagating over some huge distance, and you don't want to have a uniform magnetic field all the way through, and so you only do a pulse at the beginning, at the end, or something like that.
Right.
So are you sort of saying that that's now no longer necessary because we don't have these long distances that we're propagating over, so we can just put a cavity and do something better?
Yeah, so the idea of Ramsey, I think Ramsey explained it by a car, right? He said, like, you could have a car driving across with some really poor dampers on the springs, and you could drive across a jarabar or a sleeping policeman or whatever it's called in Italy, and the car starts shaking, and then you could do it again, and it would depend on what phase of the oscillation you were at as to whether the car went nuts or stopped oscillating altogether. And the advantage is that in that intervening period, it's just sitting there, right, in the quiet. So in an atomic system, it's sitting there in the dark. And I agree with that. But I think, so here we sort of have the same idea. I mean, we're just sitting there watching this phase evolve. And because of this destructive interference, there are actually no photons coming out of the system. But we can measure when that phase adjusts slightly. And in principle, you could go back and redefine your axes and carry on doing that sort of thing. So this is kind of like quantum engineering, you know? Rather than that simple experiment, it's like using the building blocks that we have in AMO physics to try to go beyond what is possible in that kind of Ramsey problem. So that's how I would say.
I have a question myself. Maybe it's very naive. I noticed that in the Ramsey fringes, the relative error delta F over F goes as 1 over n to power little n.
Yeah, that's correct.
To power 1. I guess also in your measurements. So why linear?
Yeah, that's true. That's a really good question. So there is a practice. Sorry, I could do this another way. But let me just quickly look back here. Yeah, this expression is kind of interesting. What this would tell you is that in order for Jin to go and measure a perfect frequency, he would like to make n infinity. So he would like to go all the way out to the end of the universe. And the problem is that this is not actually what nature gives us. It gives us this, plus it gives us dissipation and decoherence, T1 and T2 processes. And so the best you can actually do is...
the number of cycles
is limited. And once you limit it, you have to restart the experiment and redo it and redo it and redo it. And then that averages down as the square root of n, because that's just adding up independent samples. So that's the best you can do classically. The thing I showed you here can do better than that. Because...
Oh, in your method also the dependence...
Can you speak on the microphone?
Okay, please finish. Please finish. your answer.
I was just going to say you can do better than that, because the square root of n's that are coming in here are coming from independent particles and from independent trials. And in the method I showed you, the particles are not independent because you generate a spin squeeze state, and that's one-to-one with the fact that the particles are entangled with each other. And it also enables you to track forever. You can sit there continuously monitoring the system. I mean, of course, there's a vacuum chamber and the atoms eventually go away, but apart from like technical considerations, in principle, you could monitor forever.
So in your method also the dependence on little n is better? I didn't understand. My question is why capital N is under the square root, and that's fine, I understand. But little n is to power 1.
Yeah, it's to the power 1 here, but so that's the number of cycles. And that defines time, like you just a discrete version of the time. And in our case, we can take that time to infinity. That's what's meant by continuous phase tracking.
Okay, so it's very important. Not just that you improve not just the dependence on square root of big N, but also improve on that other
the measurement time
factor. Very nice. Yes, thank you. Other questions?
Just very quick one.
Can you comment a bit on the experimental implementation? So what you foresee how much you can improve with respect to the present stage?
So the first experiments on this are likely to be done in James Thompson's group. He's very interested in doing it. He's part of this collaboration. I can't speak for him, but it seems fairly straightforward to implement. And all of the models that we do actually are done for the parameters of that rubidium experiment. So, it takes time. Experimentalists are very slow, but no, but
theorists are quicker.
Yeah, but I don't see any showstoppers actually, so soon.
Okay, thank you again. I think we are done with this talk. Thank you very much again. Next talk will be by Angelo Esposito from Lausanne, sub-GeV dark matter detection with superfluid helium-4, an effective field theory approach, and this is in the field of cosmology. Ok, ti dico quando hai fatto 15 minuti.
Perfetto, grazie. Ok, how do I go full screen?
L'ora ancora non conto,
Sì. Can you hear me like this? Yes, it works. Very good. No. Maybe we'll try like this. Okay. Ah, but it's broken. Aha. Now, yes, more or less, okay. Do we have a pointer? No. How does this work? Ah. I don't know if anyone has a. I can wave my hands. It's okay. Ah, very good. Thank you. All right. Okay. So yeah, so thank you for having me here. Today I'd like to talk to you about the possibility of detecting, and it's gone, yes, of detecting dark matter lighter than the GeV using superfluid helium-4. And what I'm going to talk about is essentially based on these papers with these folks here. Okay, very good. So just a super quick outline. I'll give you a brief introduction and motivation, even if we already heard about it today. And then I'll talk about the tools that we're going to use, the theoretical tool, which is the effective field theory for superfluids. And then after that, I'll essentially analyze two possible models of dark matter and what can helium say about those, and then the usual conclusions and future plans. Okay, so as we know by now, most of the matter in the universe is dark, meaning that we don't see it. And if we interpret this as a new kind of particle, it's a strong indication towards physics beyond the standard model. However, the problem is that these particles can have a huge possible mass range And if you want to look for them on Earth-based experiments, the techniques that you want to use is strongly dependent on what mass range you're looking at, and they vary very strongly. And in particular, as we heard already, if the dark matter is in this mass range, which is typically what is called the WIMP range, then it's essentially heavy enough to be considered as a single particle. And it's also heavy enough so it can release enough energy on the nuclei of whatever detector you're using, and maybe you can detect that energy release. On the other hand, if it's very light, say here, you can consider the dark matter has a coherent field, as a classical field, and then you can use coherent effects, like resonances and stuff like that. The problem is in between here, in this what's typically called the sub-MeV region, sub-GeV region, because the dark matter is heavy, so it is definitely a particle, but it's not heavy enough to release appreciable energy to any detector you want to build. Okay, and there are a lot of ideas that have been put forth. It's very interesting, it's super exciting, it's a new field. And one of these ideas is to use superfluid helium-4. And helium-4 has different advantages. One of them is that, of course, it's a light nucleus, so it maximizes the energy that you can release to the system, right? And it also features gapless excitations, which is what we're gonna employ. And gapless excitations, by definition, they are easy to excite. And finally, it's cheap. It's very cheap, and it's almost pure against radioactive decay, so that's good. And the original idea about these was proposed by the group at Berkeley, and the idea is that the dark matter can go through helium, emit a certain number of collective excitations, and maybe release enough energy to be detected. Okay, very good. The problem, however, is that the standard approach to the dynamics of helium-4, it's complicated, because helium-4 microscopically at the atomic level is a strongly coupled system. And so if you want to go from the atomic level description to the description in terms of phonon, using the most standard techniques is doable, but it's a bit hard, okay? But there is an alternative way, which are these effective field theories for the superfluidity, for superfluids and other states of matter, which is what we're going to use. And in my opinion, to use this tool has some advantages. One of them is that you are formulating the problem in a quantum field theory language, which means that you have actions, amplitudes, Feynman diagrams, and so it's easier to deal with if you have a particle physics problem, like the one at hand. And secondly, it's also important because all the couplings of the effective theory that I'm going to show you are determined by the equation of state of helium-4, which is something that has been measured, okay? So from this viewpoint, I don't really need a microscopic theory that I use to derive this coupling. I just go and I measure them from data, okay? And then since it's mostly based on symmetry arguments, I can actually typically extend it to other models of dark matter as well. Okay, so let me give you a brief introduction of this effective theory. If you go and look for the dispersion curve of helium-4, namely the energy of its excitations versus their momentum, okay, it typically looks like this. You have a linear branch here, which are the phonons, okay, which are essentially sound waves, and are gapless, meaning that at zero momentum they have zero energy. And then you have other features, and these excitations are called maxons, rotons, and so on and so forth. And let me stress right away that whatever I'm going to say, it's only for the phonons, because these effective field theory that we can write down, they are low energy effective field theories, and they cannot incorporate this branch here, okay? But the bottom line is that it turns out that the phonon is nothing but the Goldstone boson associated to a certain number of broken symmetries, spontaneously broken symmetries for the helium. Now, unfortunately, I don't really have time to show how you build the effective theory, but if you want, I'm happy to discuss about it later, or I have backup slides or whatever. But the bottom line is that we know what the symmetries of helium are. In particular, helium has a certain conserved number of particles, and it's at finite density, and that we know. And from the FT viewpoint, it's a system that breaks spontaneously, and that's the crucial point, boost time translations and the U1 symmetry, but preserve a certain combination of them. And as you typically do in EFT, once you know the symmetry breaking pattern, you can write down your interactions for your Goldstones, which in this case are the phonons, okay? And the first model of dark matter that I'll consider, because then, of course, what I just told you is sufficient to describe how helium behaves by itself, right? But now we want to have the dark matter together with helium, because that's what we want to measure. So you gotta also tell me how the dark matter talks to helium. And the model that we consider first is a model where the dark matter, which is what I'm going to call chi, interacts directly to the helium density, okay? If that's the case, you can apply your EFT techniques and derive an action. You don't have to go through the details. The only point that I want to stress is that this action incorporates the interactions of the phonon with itself and of the phonon with the dark matter, okay? And so I can go through the usual particle physics, high energy techniques, okay? And all the couplings here are completely determined by, say, the sound speed of helium. This is gone, I think. It's okay. I can point you to the sound speed of helium or the number density or the derivative of the number of the sound speed with respect to pressure, but it's all things that have been measured, okay? So about this action, we know essentially everything but the coupling with the dark matter, which is precisely what we want to measure or constrain. Okay. Before going to the actual observables, we gotta ask ourselves, how do we see phonon and can we even see phonon, okay? And so my naive understanding is that there are two possible ways that have been put forth. The first one is through this quantum evaporation, meaning the phonon, after being emitted, it could travel up to the surface of the helium. And if it's energetic enough, it could eject one of the atoms out of the surface. And by energetic enough, I mean that it has to be more energetic than 0.62 millielectron volt, which is the binding energy of the helium atom to the rest of the surface. Okay? It goes on and off. Okay, thank you. And if I understand correctly, it's okay, I got long fingers. And if I understand correctly, this is probably the most promising idea. There is a lot of effort going on, R&D and so on and so forth. The other idea is just the classic energy release, meaning the dark matter goes through, emits a certain number of phonons, which eventually heat up the system. Thank you, grazie. Yes, very good. Which eventually heat up the system. And maybe you can measure this change in temperature using bolometers. And to the best of our sensitivity today, this can be done if the energy released is larger than 1 millielectron volt. Okay, so this slide is just to say that there are R&D efforts going on both sides, bolometers and quantum evaporations, and there are people putting effort and money in those. Okay, so now we can move on to the actual observables. The simplest observable is the emission of a single phonon, meaning the dark matter goes through the helium and emits one phonon, okay? And this is something we can compute easily with EFT, just because it's a standard particle physics problem, okay? This is a nice observable, because of course it's dominant, in the sense that it's easier to emit one phonon than to emit two, but on top of that, it's also directional, because since the dark matter is much faster than the sound speed in helium, if it emits a phonon, it does that at Cherenkov angle, okay? Which means that in principle, if you're good enough, and you can reconstruct the direction of the phonon, then automatically you also reconstruct the direction of the dark matter. And in particular, if you use these quantum evaporation techniques, there is a hope that you could measure the direction of the phonon. The angular spread is not that big. Okay, the drawback of this process is that kinematically is only allowed, essentially, if the dark matter is heavier than roughly 1 MeV, okay? If we want to go below the mass range, then we gotta use another process, which is the emission of two phonons. Because in this case, there are kinematical configurations, there are configurations of the two outgoing phonons that allow you to measure the event, even for dark matters that are as light as 1 keV. And the nice thing is that this process can in principle be detected both via quantum evaporation and energy deposit, which one might use to discriminate what's happening, whether you have single phonon or two phonons having some sort of trigger based on these two things. And from the EFT viewpoint, the amplitude for this process is obtained with these two diagrams, which we know perfectly how to compute, okay? And as you'll see in a bit, it's actually very important that there are two diagrams rather than just one. Okay, very good. So the first bit of information is that for this two phonon process, you can study the angular distribution of the final phonons, okay? And ask yourself, how does it look like as a function of the dark matter mass, okay? Can I know something about the dark matter by studying how the two final phonons look like? And it turns out that the lighter the dark matter becomes, meaning in this direction, the more back-to-back the final phonons are. In the limit where the dark matter is super light, then you emit phonons exactly back-to-back, meaning that you are transmitting energy to the system, but you're not transmitting any momentum to the system, okay? And this will be very important. Very good, given that we can cook up everything, it's not hard, and you can build up an exclusion plot. So just to explain what this is, everything above these lines is excluded, okay? Meaning that if we build a helium-4 experiment, either you see dark matter above these lines, or that's it, okay? If you don't see anything, it doesn't mean that dark matter is not there. It means that, for example, for this mass, its coupling is less than this, and so on and so forth, okay? And here we have the curve for the single phonon, which is dominant, but as I told you, fails at 1 MeV roughly. And then we have the curve for two phonons, which instead allows you to go as down as the KV, okay? And there are two crucial points here. The first one is that we are able to reproduce the results obtained by the Berkeley group, okay? But there is a crucial bit of information there, meaning that in this calculation, you include both phonons and higher excitations like protons, okay? But while we don't, okay? And the fact that we don't tells us that to this process, the main contribution comes from phonons rather than protons. And if I understand correctly, this is a crucial bit of information for experimentalists. If they want to design some device, they need to know what should they be looking for. Should they be looking for protons or should they be looking for phonons? It turns out that the answer is that they should be looking for phonons. And the other piece of information is that if you plot what you would naively expect just from phase space, meaning without having the information from the EFT, it turns out that the actual rate is suppressed by almost 10 orders of magnitude with respect to just phase space, okay? And the question is why? And with EFT, we can understand why. First of all, as I told you, you have these two diagrams. The first thing you can do, you can just look at these two diagrams at face value. Remember that for very light dark matter, meaning that for dark matter in this region, okay, you are essentially in a back-to-back configuration. And if you put yourself in that regime, it turns out that these two diagrams, they cancel exactly each other. And especially, in particular, when you release a little bit of momentum, these diagrams are suppressed, okay? But the EFT allows you to do more. It allows you to understand why that happens. And the reason is that this is a consequence of nothing but the conservation of the current of one of the symmetries of helium-4, okay, of the U1 symmetry, the conservation of number of particles. But you also understand another thing. This only happens if the coupling of the dark matter to helium happens exactly through the number density, as I told you before, as it happened here. We showed that if you change this coupling even a tiny bit, then your exclusion plot does better by orders of magnitude, okay? So I don't know, I think it's an important piece of information, especially for model builders. Okay, so that's pretty much it for the first model. Now let me go to a second one. The second model, it's a model where instead of interacting with the number density, the dark matter is again charged under some new charge, okay? And interacts with the standard model through some new vector boson, okay? Some new photon, which we call the dark photon, it's called typically the dark photon. And this dark photon, what it does is to interact with the standard model, it mixes with the standard photon. So the interaction dark matter to standard model happens through the emission of a dark photon, which then mixes into a photon, which then interacts with helium. And which means that if you want to study this case, you need to know how to write down the interaction between the photon and the phonons, or the helium, okay? And without going through the details of these, you can again write down an effective field theory, okay? Of course, helium is not charged, which means that it doesn't have direct interaction with the photon. You can only interact with the photon through higher multiples, okay? Which of course means that the interaction will be suppressed. And this is it, you write it down. This is the mixing that I was telling you about. Very good, thank you. Between the photon and this new dark photon. This is the interaction of the dark matter with the dark photon. And essentially what you are interested in constraining is this parameter epsilon and this coupling G. And this piece here is instead only for standard model. This tells you how the photon interacts with the helium-4, okay? And again, just like before, I was able to determine my couplings in terms of sound speed, number density, and the equation of state. You can do the same thing here. You can determine these two parameters here, A and B, which are the only things that you don't really know, in terms of the properties of helium, and in particular of its electric polarizability and number density. And again, once I know these, I can write down an action, I can expand these, write down amplitudes, and so on and so forth. The first nice thing about these is that what I can do, I can introduce an external, say, electric field in the game, okay? Because if I do that, then I'll slightly polarize my medium, and I'll make it easier for the photon to interact with it. And you can do that, and we can study again the process of emission of a single photon by the dark matter, but in presence of this external field. And once you do that, this has the nice property that now you have a preferred direction, which is the direction of the external field. And your amplitude, and in turn your emission rate, depends on the relative angle between your electric field and the incoming dark matter, which gives you a good background rejection, because now if you're wise enough, you know where the dark matter is mostly coming from, you can rotate your electric field with time, and if you do that, you expect a modulation in your signal, which otherwise you wouldn't expect from a completely isotropic background. So you can use that to discriminate your background. And that's it. After that, you can play the same game and see what helium tells you about this model. The first thing that you notice is that this is not, so if you want to look for a dark photon dark matter, helium-4 is not the best experiment you have, because it's only competitive with the current bounds if you are thinking about a dark photon that is very heavy, very light, because it has to be so light that it evades bounds coming from the CMB or from supernovae and so on and so forth, in particular lighter than 10 to the minus 13 electron volts. But if that's the case, helium can do a bit better with respect to the already existing experiments, Sensei, Xenon 10, and Xenon 100, but in a very limited scenario, okay? But, you know, it's better than nothing. Okay, so just to conclude, I think a helium-4 experiment for the search for sub-MeV dark matter is promising. It's a promising direction, but it's also sort of exciting because there is a lot of R&D to do, especially on the detection of phonon side. And I believe that the EFT for superfluids, it's particularly simple and it's particularly suitable for what we are interested in right now, and it can maybe provide a key tool for future investigations. And of course, there are a lot of other directions that one could follow. One could look into other materials. For example, we're looking into the emission of optical phonons in polar materials, in crystals. Or you could think about these crystals that have very strong natural electric fields inside, which could enhance your probability of emitting dark photons or whatever. Or maybe you can even think about other devices involving helium-4. For example, can we employ the fact that helium-4 has a phase transition at a certain temperature, and so something is drastically changing. For example, its viscosity, or emission of other excitations like vortices and so on and so forth. And I'll stop here. Thanks.
Tens of seconds. And any questions on this nice talk? Please. Momento.
So you made a statement about the process where you emit two phonons, and you said that the dominant contributions, comes from phonons rather than from protons. Strictly speaking, is there a statement at T equals 0? Do you have a sense of how that would change if you go to temperatures that are non-zero or below the transition?
It's definitely a statement at T equals 0. No, I don't know how much would that change, but in all fairness, you're talking about production of collective excitations. Now, what's happening when, I don't know, but what's happening when you increase the temperature is that you increase the number of thermal excitations, right?
That's right.
But that would be a different process. It would be the scattering of the dark matter of a thermal excitation which is already present, I would say.
No, I was just thinking, like in stimulated emission, if you have already excitations around, that can affect how much you produce, right?
No, that honestly, we don't really know.
Yeah, you made that comment about the case in which dark matter couples to the density, and then you have a cancellation in the, so that's just corresponds to the case where it couples exactly to the current, right? This is the...
Or even, even just if, for example, if you couple to the trace of the stress energy tensor.
Sure, that reduces to...
Yeah, as long as in the non-relativistic limit you have something proportional to the number density, then you have the cancellation. Of course, in that case, you could have an enhancement due to the fact that if you have the trace of the stress energy tensor, the coefficient in front is the mass of the helium rather than the mass of the dark matter. but the cancellation still happens.
Hi. Maybe you already explained this, but why helium-4 and not one Bose-Einstein condensate?
Any other? Or you mean like cold atom stuff?
Yeah, cold atoms. Bose-Einstein condensate also has phonons.
Yes.
It's even much colder, actually.
But my understanding is that you need the stability of the experiment that is long enough to see dark matter. These things are going to last years, so you would need a cloud that you can keep there for.
You need many atoms.
You mean what?
You need many atoms.
You need many atoms to increase your cross-section, essentially. But you also need something that can be there and you can wait long enough to see.
Okay, so it's a time limitation, I would say.
Typically, these experiments are very big and you keep them for a very long time.
Okay, the time is the limiting case, okay.
Any other questions? I have a comment.
Sure.
You mentioned in these last slides using other materials. Of course, you are just trying to detect something. Yeah. So, but I think you may be interested in another aspect of the interaction of dark matter with matter. And that, you know, our reconstruction of dark matter in the universe, our explanation of how much we should expect is based on the assumption that it interacts with ordinary matter only gravitationally. Mm-hmm. And some people have been trying to see if this is true using an equivalence principle instrument looking at the center of our galaxy to see if dark matter in the center of the galaxies interacts in the sense of producing an acceleration on the test particle differently. Mm-hmm. And I have reached 10 to the minus 5, which is not much in terms of equivalence principle, but it's very interesting. Yes. Because it means that that's the level that we currently know at which we can tell that dark matter interacts with ordinary matter only gravitationally. Mm-hmm. Of course, I do not expect, I guess, that if you use some other material, you will, here the point is either you see something and detect dark matter or not. So
No, but in fact, the idea of using different materials would be to cover different mass ranges, essentially.
Yeah,
but
exactly.
The basic idea is always
your point is to see something. Yeah, exactly. So, but it's interesting, I think, to know this aspect of our understanding of dark matter and how it works. Sure. Okay, thank you very much. Let's thank him again. Now we have, Gregorio Carullo, who will tell us about observation of black hole spectroscopy, and that's cosmology. And then we have coffee.
Okay. Okay, I'll start. So, good afternoon, everyone. I'm Gregorio Carullo. Sorry. Where the microphone? Oh, sorry. Okay. Is it okay? Okay. Okay, so I'm a PhD student here at the University of Pisa, and I'm part of the Virgo data analysis group in Pisa. So I'm part of the LIGO-Virgo collaboration. And so I have 20 minutes to keep you away from coffee, And in these 20 minutes, I'll try to use my time wisely, and I'll try to introduce you to a subfield of gravitational wave astronomy, which is called observational black hole spectroscopy. And I will try to tell you what kind of, not only what observational black hole spectroscopy is, but how we can use it to test the theory of general relativity. Okay, so after a brief introduction of quasi-normal modes of a black hole, I will highlight the first measurements when this field was born in 2016, when the LIGO and Virgo collaboration published the first measurement of ring down. And after that, I will start to elaborate and tell you how we can improve this measurement, what tests of GR we can do with second-generation detectors, means LIGO and Virgo, and Kagra and LIGO India. And finally, how we can use population inference to enhance our sensitivity to detect deviations from GR. Okay, so well, I suppose all of you know roughly at least what this plot means. So these the detection is the first triple coincidence, so it's the first detection when also Virgo saw a signal in coincidence with LIGO. And so this is a time frequency reconstruction of the power in the detectors, and this is the strain. So it's the relative allongment of the arms in the interferometers, which tells you how much the space-time dilated essentially. So it's, and we call this waveform. So let's try to elaborate a little bit what this waveform is, how we can understand the different bits. So this waveform is roughly made of 3 parts. So the first part is called in spiral. So it's the moment where the 2 objects are orbiting each other. They are far away, so the interaction is weak, or at least the evolution is adiabatic. That's the correct description. So the frequency is slowly rising, and you can describe this in an analytical way. Then there is the very violent phase where the 2 objects merge one into each other, and they form a common horizon, and it's called plunge and merger. So they plunge into each other, they merge into a single common object, and this is in the highly nonlinear regime of GR, so you need numerical simulations. And finally, there is our favorite bit, which is ring down. So you already formed a single final object, but this is not still in a stationary state. So it wants to relax towards a Kerr state, but it's still very anisotropic. So it's radiating away all its anisotropies, emitting in the form of normal modes, of quasi-normal modes. So we are going to analyze essentially only this bit of the waveform, which is very small, has a very small signal-to-noise ratio, but it's very interesting. It encodes a lot of physics. Okay, so what is ring down? So ring down is, to understand what is ring down, you have to remember that in GR, space-time is a dynamical entity, so it will have oscillatory solution even when no matter is present. So if you have a well-localized object, you can imagine that this object will have quasi-normal modes. So ring down is essentially the emission of the normal modes corresponding to the black hole. So it's a signature of the metric. So it encodes the structure of the metric in the frequencies and the damping times. The analytical solutions of linearized Einstein equations on black hole background were found in the late 50s and then 70s for the spinning and non-spinning case. And I'll briefly sketch how we can how you can derive it. So essentially you take Einstein equations, you take a background metric, which now is Schwarzschild or Kerr or whatever you like. Then you take some linear perturbation around it, you plug it into the Einstein equation, linearize, and you get this wave equation with this potential. So this potential has a lot of interesting properties, which I'm not going to describe because I don't have the time. But the thing I want for you to notice is that it peaks at the light ring, so the last stable photon orbit, and it decays to infinity. So minus infinity is on the far left, and plus infinity is on the right. Well, my left, and yeah, your left and right. So plus infinity is on the right, and at plus infinity it decays very slowly, which means that the curved background here is playing a role. So you will the gravitational wave which impinges from plus infinity, it will start to see the black hole even far away from the horizon because the curved background is interacting with it. And so this is a sketch of what happens when you take an isolated black hole and you throw into it something. So we are throwing it a Gaussian packet, which gets deformed, interacts with the black holes, and some part of it is reflected away back to plus infinity. And what is reflected away as a typical form, which is a damped sinusoid. So Gaussian packet, some of it goes into the black hole, some of it gets reflected away. And what gets reflected away is a damped sinusoid. So what happened is, so you have to think of the black hole as a filter. So you can throw into it whatever frequency you like. It's going to filter it, so it's going to absorb every other frequency and re-emit only its own characteristic frequency. So it's going to re-emit its quasi-normal modes frequency. I call quasi because it's not a sinusoid, it's a damped sinusoid, because there's damping both from the horizon and from the fact that the gravitational waves escape. And well, that's pretty much it. So what would you see here on Earth if you would well, detect ring down? You will see this kind of waveform. So you'll see essentially a sinusoid which is damped. There's a lot of other information which I'm going to skip. So, but the key point here is that so you will have a superposition of different modes, which are angular modes. So I'm decomposing in angular modes, Lm, and then there is this n index, which is the higher harmonics, essentially. But the point is that the frequency and the damping times of all the modes are only function of the final mass and final spin. So of the mass and spin of the final remnant black hole. Which means that you have to measure, if you measure two quantities, you will predict the whole spectrum of the black hole. So let's say that I find a way to measure two frequencies and one damping time. From the two frequencies, I can get a measure of the mass and spin, and then I can predict the third damping time. So with the third observation, you now have a new independent observation. So it's 3 observations and 2 parameters. Okay. So the third one is constrained, and once it's constrained from the theory, you can test GR. That's the key point. So the key point is that with high sensitivity enough, you can then test the prediction of general relativity on this spectrum. Well, I'll just try to make you curious about one thing. So what if there's not complete absorption here? So here at minus infinity there is an horizon, but what if there's no horizon? What happens? Well, what happens is called ecos. So if you do not have an horizon, so you have some sort of absorbing barrier, but not completely absorbing. So it's not a black hole, it's something different. It could be an exotic compact object, it could be some quantum effects on the horizon. There are a bunch of proposals in the literature, but this is very, very interesting for a lot of theorists. It's very, very well studied. But what happens is that it happens that you have a barrier and then the potential. So after the first burst of the ring down, some radiation will travel to the barrier, gets reflected and go back. So you will have multiple reflections of this radiation, and they will produce not one ring down, but a lot of bursts of ring down, which are called echoes. And I will send you to this review if you're interested in this. Okay, so that was the brief outline of the theory, which is very active. So if you search the archive every day, you will find at least 2 or 3 papers on quasi-normal modes, I can guarantee you that. But let's talk about observations. So this is the first, and until a few months ago, I would say, it was thought that it was the only ring down observation that we could have, but actually you can observe ring down in many more signals. And so it's a probability distribution on the frequency and the damping times from the first observation. So the dotted lines, so the solid black one is the prediction of GR, and the dotted lines are the measurements that you do from the final bit of the waveform. And there is an ambiguity here because you need to be in the linearized regime where your approximation of linear ring down is valid. But of course, in a binary black hole coalescence, you don't know where it is. So you have to start at different times. And when you are late enough, then your approximation will be good and you will encode GR. But if you start late enough, everything is consistent with GR, and that's easy. So, but this was a modeled analysis. It didn't exploit all the available theoretical information. So it's improvable in several ways. And the systematics were also pretty much unclear. So how can you push that analysis forward? First of all, you have to switch to a time domain likelihood, which is different than what LIGO and Virgo usually do. Then I think it's convenient, but for me it's imperative to reformulate black hole spectroscopy as Bayesian model selection. Then you want to identify ring down in other signals, do population-based tests of GR, and test the Noether theorem, possibly already with these detectors. So let's go directly to the results. So what we did in a recent paper, so we redid that analysis, and the reconstruction of the waveform is here. So it's a now nice damped sinusoid. We also reconstruct the sky position, which is a technical point, because the sky position is it's correlated with the time of arrival, so it's correlated with the time of ring down. So it's a very tricky bit that nobody was able to reproduce before this work. But then the money plot is this. So this is what we call black hole spectroscopy. So what you call black hole spectroscopy is this. You measure the initial parameters of the binary, initial mass and initial spins. You predict what the spectrum of the final black hole should be. And the spectrum are these colored, well, they would be ellipses, but these colored lines, let's say. So GR has a full spectrum of ring down modes. And so they are angular modes. So it's the 2-2, which is the quadruple, then the 2-1, 3-3, and so on. So you predict what the spectrum of GR should be. Then you measure from the last bit of the waveform, agnostically, what the frequency and damping time content is. And that's it. You didn't impose that it was a black hole. You didn't impose that GR is true. Nothing. You just suppose that there was a damped emission, which is, of course, mandatory given the data reconstruction you have. But there could be an alternative theory, there could be a gravastar, there could be whatever you like. There are a wide range of possibilities that can modify that frequency emission. And then you can compare, of course, this agnostic reconstruction with the prediction of the spectrum of GR and see how much they are consistent. So it's an application of Bayes' theorem, and what you get is this other plot. So this now is a 3D plot because of the problem I told you before. So there is this systematic uncertainty in the start time. Here it was partially resolved because we marginalized over it, but it still depends on the prior. But the idea is that if you start late enough, the frequency at a certain point, well, at a very reasonable point, starts to be consistent with GR. And so what this plot tells you is that if you start very early, you're going to think that you detected a very strange mode, which you would not expect from GR. But then if you start late enough, you will detect essentially what you expect. With one caveat, which is you are not able to pinpoint a single mode. So if people tell you, yes, we measure the quadrupolar fundamental mode, which is the 2-2-0, that's false. You cannot prove that it was the 2-2-0 fundamental mode. You can prove that it was consistent with either the 2-2 or the 3-3. So it was consistent, very consistent with what the fundamental mode would look like, but you still cannot pinpoint a single mode with that observation, which is the first one. You can recast this in terms of mass and spin. That's easy. We don't care. But what you can do is that you can start asking yourself, okay, can I detect more than one mode? And the answer is no. So this log bias factor essentially reports the probability that you detected one mode or the other. And so from these numbers, you can essentially tell that you have no evidence for more than one mode, so you still cannot rigorously test the Neuer theorem. Well, yes. So this is what you can do for the analysis. So this is the analysis itself, because to test GR, first of all, you have to have strong control on the standard case, which I hope I told you we have. So once you have the measurement, let's say in the systematics under control, then the next step that you want to do is to test GR. And this is the result. So how do you test GR in this context? You have a frequency spectrum, which is, so these frequencies, which are parameterized by mass and final spin. You change them, and you insert a parametric deviation. So it's a percentage deviation. It's a delta omega in each frequency. And you want to measure this delta omega. So if this delta omega is consistent with 0, GR is OK. We measure the spectrum of GR. Everyone is happy. So last year, I think, Professor Trincherini showed predictions for the frequencies in, I think it was scalar tensor theories. I don't remember. But the point is that there are a very large range of alternative theories or alternative objects which predict a shift from the GR spectrum. Well, now whatever theory you have, it must be compatible with what we are measuring, and we will measure. So the bound on the percentage deviation of GR now is very broad. So it's essentially this posterior distribution. So this is the deviation, this is the probability distribution. It peaks at 0. We are happy. GR is correct. But the point is that the constraints are very, very broad. So it's plus or minus 50% than what GR predicts, which is, well, not good enough. So one could tell you, okay, I don't care about a 50% deviation. I know I'm not going to get a 50% deviation. My theory predicts 1%. So what we did then in another work was to predict what kind of precision we will reach with LIGO and Virgo at design sensitivity. And the number is essentially 1.5%. So with a few golden events, so with 6 good events, we're going to reach the 1% level, essentially. And this is consistent with what the group of Alessandra Buonanno at Max Planck also did. Okay, of course, you can do the same thing on tau, on the damping time, and then you can do the two of them together. There is no evidence for modified gravity yet. Well, so the common knowledge was that ring down was only observable in the first event, which is 150914. That's false, and this is the proof. These are 2 other events in August of 2017, and you can very precisely measure the frequency of the ring down in these other 2 events. So once you did it for one, you have everything under control. You do for all of them, and you want to put them all together to get a combined constraints from all these events. So the first way of doing this, it's a null test hypothesis, let's say. So it's a way of asking you, what is the statistical error that I have on the GR0 measurements? And so you can just multiply all the likelihoods together and get a combined constraint. It's slightly better than the previous one, so it's minus 25% plus 50%. So you reduce your uncertainty of 25%, which is okay, but still it's not the best thing to do because these assume that GR is correct in some sense. So it's a null hypothesis. What you want to do is called the hierarchical analysis. So the idea of a hierarchical analysis is that in a genetic theory of gravity, the deviation, so the shift from the GR spectrum will differ. So some binary will have a shift of plus 0.1, some other of minus 0.1, and so on. So every shift will be different because the binaries that you measure have different initial masses and initial spins. So you cannot multiply posteriors because you would be multiplying 2 posterior distributions which are picked at different values, and that will give you 0. But what you can do is that you can think that there is an underlying parent distribution, whose shape is given by the alternative theory of gravity, and you can put constraints on this parent distribution. So every measurement you make on each binary is a realization of that parent distribution. And of course, the GR case is the delta distribution centered on 0. So you do this analysis, and you get very similar measurements to the GR null case, but this plot does not assume that we have that GR is the correct theory. It's fully general in the sense that if a theory gives you this kind of parametric shift, it will catch it. Yes, so this is the combined case. So I'm gonna try to conclude, and in concluding, explain you why these kind of measurements are, according to me, very, very much important. So black hole perturbation theory is a very well-established theoretical framework from the 70s, essentially. And theoreticians like ring down very much because it's easy, and you can do it for a bunch of generic different theories and alternative compact objects. So this is a very active field. And nowadays, since 2016, black hole ring downs are measured routinely from the Eigen-Virgo collaboration. And what we showed is that tests of GR using ring down are possible with second-generation detectors, but their constraints will not be extremely interesting. So what interesting constraints could come either from third-generation detectors, so Einstein telescope or Cosmic Explorer, whatever you like, or from space detectors, of course, with one caveat that nobody mentions about LISA, is that, so I love the measurements that we will be able to do with the LISA experiment. It will be an extraordinary precision, maybe orders of magnitude more precise than what we do. But there's just one caveat. LISA sees, for ring down, supermassive black holes. And supermassive black holes explore a regime of much lower curvature. So these comparable mass black holes are in a regime of much higher curvature because they are smaller and with comparable mass. So LISA will have precision measurements of these kind of parameters, but in a regime of very different curvature, which is much lower. And I will leave you with the slide of why do we need to do this, because once you do this, so once you do the measurements I showed you, you can test Hawking's area theorem, the uniqueness theorem, the energy and angular momentum conservation during the strong field emission of GR. You can extract implication, of course, on the astrophysics, but you can test for the presence of alternative compact objects because the normal modes are the signature of the black hole metric. And you can also, some recent work has shown that you can constrain the graviton mass, or maybe, and this is a very interesting possibility, you can test quantum horizon effects and classical black hole thermodynamics. So if you want to know more about this tomorrow, Denis Laghi is not here, but Walter Del Pozzo is going to present a work on testing the area quantization hypothesis using this analysis. And yes, that's it.
Thank you very much. Very interesting. Any questions? Please.
You emphasized in your talk that you're testing GR, but don't the other parts of the gravitational wave signal also check strong gravity?
So, okay, so you can test GR in many different ways. That is not the only way of testing GR. It's a way to test GR. So another common one would be in the in-spiral regime. So the one I showed very early. Well, I don't have time to, well, I can try. So if you look at the in-spiral regime, you have analytical expressions for this part of the waveform. So you have some what's called post-Newtonian coefficients, and you can put constraints also on those post-Newtonian coefficients. So for example, you can ask yourself, are these black holes really black holes, or they have a tidal deformability? Because if you measure a tidal deformability for these objects, then they will not be black holes. So there's a lot of ways of testing. There are different ways to test GR. This is the bit we are interested into because we think ring down is instrumental in signatures of many different alternative theories and different compact objects could appear in the ring down. But
well, does the ring down somehow probe the event horizon or something like that?
Well, technically, the ring down probes the light ring because the potential is picked at the light ring, not the event horizon. But there are some claims, there are some scenarios where the ring down carries signatures also of the horizon. One is the ecos, one is the thing that Walter is going to talk about tomorrow. There are some others which are, some of them are shaky, some of them are more solid. But yes, but the ring down tests the region which is very close to the final remnant object. Yes, but it's not the only way. That's.
I have a slightly related question. I understand why you like the third phase, the ring down. It's really very beautiful. But I wonder the second phase, the plunge merger phase, which looks really horrible, I mean, very hard. How does it influence? In ring down, you need only mass and spin, but is there any dependence on what happened in the second phase? Okay. And do you need something? If nobody does the plunge merger phase, can you still do your ring down work just the same?
Yeah. So yes, because there is this. So the nice thing is that what you need for ring down is you need these amplitudes which encode the initial conditions. So what happened before you don't care. Everything that happened before is going to be encoded in the amplitude of the.
And where do they come from?
Okay. So where do they come from now? So the way you can predict them is to measure the initial parameters of the binary. So the initial black holes here, and they will have some ratio, some mass ratio, some different spins.
So the post-Newtonian phase, somehow it's enough for you?
Yeah, technically it's enough.
You are lucky.
Yes, but no, so technically you want the merger because the higher portion of the SNR is here, because it's the most violent and most loud phase. So we can use that using numerical simulation. It's just, so actually some tests use it, for example, the IMR consistency test. So where you essentially take the whole waveform is split into, and you check the consistency of the waveform. It's just more difficult to convert the constraints from the merger into some parameter which theoretician can predict for alternative theories.
But you don't use it in your work?
Personally, I don't use it. There are some other tests from the Ligon-Virgo collaboration which use it. It's just more difficult to parameterize it, so it's more difficult to project the information that you extract from the phase on something which is computable by other people.
Thank you very much. Other questions?
You mentioned ecos, and there have been in the past in the literature claims that ecos have been seen. Bold claims, I would say. Yeah. I would like to have the point of view of someone looking to this stuff from operation.
So it's you're referring to the works of Ashford and the other group, those people. So it's more than one paper. Yeah, because they also did it for the different kind of analysis. Yeah. So, okay, there have been claims that ecos have been seen in LIGO. So the first claim was on binary black holes, and it was rejected by a paper from a data analysis scientist who did the analysis in the proper way, because the idea was very nice, but those are theoreticians, and the analysis was shaky, was at best shaky. And so a guy from Max Planck in Hanover redid the analysis properly with computing taking into account the background of LIGO and whatever, and they showed that there is no evidence for ecos. Then they redid it again for I think it was the binary neutron star or whatever, I don't remember. And then I think there was a paper from Paolo Pani, Valeria Ferrari from Rome, so theoretician who showed that the other theoreticians were not doing the correct thing. So there have been a couple of claims, but none of them have been substantiated by further analysis and by people who do this kind of analysis routinely. So, well,
the Valeria Ferrari paper claims that there is evidence for eco compatible with a star at the good value.
No, so okay. The point was that the guys Ashfordi and the other people were saying, okay, if we see echoes, we are gonna see that's a fuzzball or whatever you like. That's a very, very strange alternative object. What they showed is that if you see echoes, it can be not only a fuzzball or whatever strange alternative theory of gravity, but it can also be just a very, very compact star, which could still be compatible with GR. No, so they rejected this other bit of the claim, but from just the analysis point of view, every time the analysis was redone in the proper way, there was no sign of ecos. And actually, in the LIGO Virgo collaboration, there are now it's 3 pipelines which actively search for ecos on each signal. So it's something that we also take into account, but there's just been no strong evidence for them.
Thank you.
So since we are allowed to ask you about other people's papers, So, there was also recently a paper by Sol Tukolsky and collaborators that claimed they saw in that event 1509 also the first overtone. So what's your take on that?
Yeah, okay, so you're very much updated with the literature. So, okay, so we are in contact with those people. They actually, they do two things differently from us. So first of all, they consider also this N index here, this overtone index. So they do not search only for the fundamental mode, they search for overtones, so higher harmonics. And then they use a slightly different analysis method. So they actually recently incorporated their analysis method into our code so that we can compare and test things. So that's an analysis that is still ongoing, so I'm not gonna say anything about that. But so their claim is possible, but there are 3 points to consider. First of all, it's not new. If you take Maggiore, the book on gravitational waves volume 2, at the end of the chapter on ring down, Michele Maggiore writes, if you add overtones, you're gonna get a much higher agreement on the wave in the ring down. So it's something which, well, it's in a textbook, right? So it's something that people must have known before. Effective one-body people knew it, and they actually included overtones in the first EOB models. But then what they saw is that the inclusion of overtones was not stable over the whole parameter space. So the guys did it just for one simulations, and the idea from effective one-body people is that you cannot do it for the whole parameter space, if I understood it recently. But then, and the third point is, so it's possible, I just think it needs more evidence, much more evidence and much more detailed study. And actually, yesterday, it came out, a paper from Paolo Pani, Jimenez Fortes, and Shweta Bhagwat from the group of Rome, which they cast strong doubts on the model that they used. So they do not say it's wrong, they say that there are a lot of ambiguities which you need to resolve before taking that proposal into account, seriously. So I don't say it's wrong, I just need to say that there's much more work to be done for me to believe in that result.
Any more questions? Oh, yes.
Good.
Is there any expectation, is there any way to estimate the expectation for the delta omega in the firewall scenario?
So in the firewall scenario, I think you would be more eager to search for echoes because
So you think that in the firewall scenario, I'm just asking the thing that you measure, you don't think that delta omega is what is parametrically suppressing it then?
Okay. So
say it's small, it's just not enough. You say it's suppressed by parametrically this and this ratio.
No, well, then I ask you a question back. So in this scenario you have in mind, is the light ring structure of the Kerr black hole affected?
I mean, I'm not an expert. I'm just asking whether you guys are thinking.
So the point is that I don't think it's going to be affected because I think that the light ring structure is not going to change much, and that means that the ring down itself is not going to change much. But you will see echoes. So you will not see directly in the delta omega, but you will see in the subsequent phases. So I think that the delta omega will be very much suppressed just because the main emission comes from here, which is the light ring, is not the horizon.
So, but when you, just a very simple question, when you compute you have to solve differential equation, you have to set boundary conditions in the region around the horizon or whatever. And then if you have a firewall, I think this boundary condition may change by order 1.
Yes.
So, I see. No, sure, you have the echoes, but...
Yeah, but the point is that changing the boundary condition doesn't change the potential. So the ring down is...
It doesn't change
the potential. So if the potential remains the same...
Right, the lowest mode is the higher modes that are affected, yes.
Yes, or more than the higher modes also what I was showing you, so the subsequent reflex. So imagine there's a wave that comes from infinity, right? First there is the potential, and then there is the whatever barrier you have or firewall you have. So the first burst cannot know anything about the barrier. So the first burst must be unaffected by the barrier if the potential is unaffected, just by causality. But then if you allow for the time for the radiation to arrive to the barrier, bounce back, interact with the potential, and then go back to plus infinity, then it must know something about the barrier. So if your proposal doesn't change the potential, the first burst is going to be almost exactly the same, but then the subsequent reflections will carry an imprint. So, well, delta omega is almost.
Okay, no more questions, that's it. So we're going to have coffee break for about half an hour, a little bit less maybe, to start. Thanks. Let's thank all the speakers of this session.
For those of you who are going on top, that are going to the Piazza del Duomo for the show. And for those of you who don't speak Italian and don't understand Italian, Galileo will speak in Italian. The student will speak English, but Galileo will speak Italian. So to understand what Galileo is saying, more or less, please stick to Dario Grasso and Dario Buttazzo. Where is Dario? Yeah, the two Darios. And they will make a very good translation for you. Okay. And also for the rest, there will be some of us who will translate for you whenever there is Italian involved. Okay?
Se c'è una pennetta, se no...
No, sì, mi hanno dato questa, grazie.
Non ho capito, scusa. Io non ho mai calcolato queste cose con il mouse, ma se tu cambi la cosa cioè questo qui è il primo modo, è la frequenza più bassa, no? Sì. Non è quella che vede tutta la condizione. Cioè se io cambio condizione, se io ho un sistema e cambio condizione del contorno di ordine 1, il primo modo cambia. Sì, se io quando faccio tipo lo spettro di Kaluza-Klein, metto una roba al bordo.
Direi di sì, cioè almeno mi aspetterei di sì.
A meno che il primo modo sia un modo soppresso al bordo. Se è un modo che è zero al bordo, allora non cambia niente. Se per qualche ragione, capisci cosa vuol dire? O la sua derivata non sarà zero al bordo, quindi cioè insomma è un'equazione del secondo ordine. Scusami, è un'equazione del
Posso chiedere aiuto?
Sì.
Così andiamo. Io vorrei spostare il mio file. Dove lo devo mettere?
Nella cartellina.
Posso? Prego, prego. È questo qui, QFC2019
Faccio vedere una cosa, non so se vuoi rimanere sul tradizionale o sull'alternativo.
Temo il tradizionale.
No, perché? Questo?
Sì.
Fa così. Allora decido che fa così. Che da un lato è alternativo, dall'altro però si vede in videoconferenza.
Però uno non vede tutto il resto.
Esatto, gli altri hanno poi preferito alcuni.
No, infatti.
I primi di stamattina lo usavano perché appunto nella videoconferenza, nella registrazione rimane tutto così.
So, però...
Niente, io solo detto che c'è.
Ma quindi questo
va avanti e indietro e poi
c'è un altro
questo può essere usato come uscita.
Che invece questo non può fare anche avanti e indietro.
Sì, probabilmente togliendo questo e mettendo il suo pezzetto che non so dove l'ha. Forse lì in fondo.
Così uno c'è una cosa sola.
Vado a mettere la slide di copertura, se no vedono già.
In presenza di un campo esterno, questo si deforma e vai a misurare il campo di multipolo all'infinito. Questi sono ovviamente in presenza di campo esterno la metrica del numero cambia in modo anche che ci vai anche.
Ok, perfetto. In realtà io non sarò il primo, ma...
Allora semmai io riprovo a rimettere il mio, magari involgo qualcuno, poi può ricambiarlo tranquillamente.
Quando L diviso x minus b, gli integer sono 0, altrimenti sono 0. Sono i multipoli indotti. Cioè, tu mandi un campo di dipolo esterno, allora i dipoli vanno come anche la L o uno su L, esterno, pensavo come la facciamo l'altro, io metto il campo relazionale. Vedi come lo reagisce, per esempio la polarizzabilità dell'atomo di idrogeno è che lo metti un condensatore, questo si allunga un po', si crea un po' indotto e posso misurare quel campo di polo. Questo è il tipo di faccio la roba nera, ottengo 0, L diviso di che vuol dire che lui si deforma ma non giunge l'effetto totale di questa deformazione zero. Scusa, e allora come ad esempio se tu vai a di fronte, guardi se l'orizzonte ha una metrica indotta è una sfera oppure no. Scusa, ma l'effetto aspetta un attimo. Quella è una misura che è tutto statico, però è statico. La misura che è invarianza è la geometria dell'orizzonte. Penso io, è come se questa deformazione invece di aver fatto gli effetti di polo vanno avanti. Se la deformazione va esponenzialmente.
No, non hai una coda, hai solo il campo tidal field, cioè tu metti il tidal field e vai a cercare la coda e non la trovi perché i coefficienti sono tutti 0 per tutti gli n.
Non c'è vuol dire che il campo di risposta è semplicemente corrisponde a un campo massivo.
Vicino all'orizzonte un po' di coda ci sarà.
Ci deve essere, certo.
No, asintoticamente però non c'è, sì, esatto. Allora,
è come se il campo gravitazionale fosse una massa.
Non lo so.
Probabilmente perché in dimensione 4 poi vedere un riflettivo. È una questione di
ragionevolezza.
Scusami,
no, perché c'è anche il mistero, forse legato, forse no, della electric magnetic whatever, cioè che gli spettri dei quasi elettrici e magnetici sono identici, sebbene le funzioni d'onda siano diversissime. Io sento solo ste parole da voi.
Ma quindi c'è un effetto esponenziale. C'è un effetto, c'è un campo di reazione che decreta esponenzialmente. No,
è difficile dirlo. Io trovo c'è l'espansione iniziale dalla sessione, due condizioni al mondo. Una me la metto all'infinito che è il mio tidal field, che l'ho fissata. La condizione a bordo la metto all'orizzonte di regolarità, quindi la mia soluzione vuole essere regolare. Quindi ho la mia soluzione, che sarà una soluzione regolare all'orizzonte. Se la vado a espandere all'infinito, trovo che
tu c'è effetti di potenza a tutti gli ordini, in su R, però se tu cerchi di espandere l'esponenziale,
non è un'esponenziale, è una funzione ipergeometrica, poi non so se tu la puoi espandere come sei.
Sì, è la funzione che se tu espandi è una funzione che tu prendi e alla meno 1, quando G va a 0, potrebbe essere R a meno R. Però tu la espandi in potenza di R,
potrebbe anche essere la potenza di R.
Hai analizzato perfettamente il tempo. Immagino che c'è un
sì,
cioè R lei lo stesso puro su R lei più 1. Quindi se scazzi quella è già cioè nel senso vuol dire che decade velocemente.
È ancora meglio.
L'associazione
ci saranno di luce. Diciamo le previsioni a 24 ore di solito c'è Ora hai visto,
No, questo è vero, uno ci compriamo la vita
no, è interessante, io non seguo solo le prime cose stamattina,
che non c'è
poi devono venire
non c'è una coda nella soluzione regolare.
Quello lo so che ho già visto altre volte, è una spiegazione.
Mettici su Starci uno spin
un background a zero. Scusa, se lavori in 4 meno F, cioè si capisce che
è non 0, però è tricky perché
com'è che vedi?
Allora, il punto è, allora, se tu prendi la tua equazione è un'equazione ipergeometrica, se tu non lavori in 4 dimensioni c'è una soluzione che ha una coda. Però se tu vai in 4 dimensioni, però il problema è c'è una sottigliezza che le due soluzioni di secondo grado, le due soluzioni indipendenti, se tu vai in 4 dimensioni queste due soluzioni indipendenti sono funzioni ipergeometriche e non sono più linearmente indipendenti, è un caso del genere. Quindi
devi fare la differenza.
Devi stare attento.
E poi come quando c'hai due esponenziali uguali c'hai tipo LT e T per LT quando c'hai due esponenziali uguali.
E quindi in quel caso il limite che epsilon va a 0 ti ammazza la coda che è proporzionale a epsilon in un certo senso.
Che storia. E quello che hai dimostrato con le sue teorie effettive è che con la teoria effettiva riesci a dimostrare che se sono 0 poi con la teoria effettiva
prospettiva non li vedo mai. C'è un teorema di nuovo normalizzazione, si parti da zero, però non riesce a dimostrare che deve essere zero, perché per la teoria effettiva non è chiaro cosa vuol dire avere un punto nero, anziché avere una quindi non è chiaro come caratterizzare la nerezza. No, viene da power count per lui. Soprattutto da piazzato fuori dai grandi bottiglioni, il power count.
Noi alle 4 e secondo me e poi si va a 5
dipende dal QFC, Pirelli pari sono 0, Pirelli QFC sono 0.
Because it's going to be
anche i loro stessi. Ma perché ha a che fare con cosa sostanzialmente sull'orizzonte
e non è chiaro l'utilizzo come fare a dirgli allora
non è una specie di
ok, ci pensano loro.
Femminismo, sono ottimista, Enrico, sono ottimista.
No, non sarebbe gli altri ragazzi.
No, però vengono no, cioè no, e lì, cioè, non è semplice, perché lì metti dei coefficienti a caso, apparentemente hai dei coefficienti che dipendono da R, eccetera. Poi dici, ok, troviamo una soluzione con i capelli. Difficilissimo, cioè è difficilissimo trovare una sola soluzione con i capelli, di andare a queste teorie di Galileo 5, no, cioè, Osbonega. Perché?
Per sono cose che fa con te. Poi due, tu, lui e Ram.
Cioè, però, speriamo, ma però insomma, non è chiarissimo perché non ci siano i capelli dalla conclusione del capello. E poi ci ho pensato un po', anche
i capelli sono abbastanza rari. E io il pelo migliore.
Io non sono protetti.
Sì, entra l'orecchio e c'è
Adesso non si può pettinare come spero.
Tanto non so che ecco, magari non so.
Ragazzi, no,
va bene, allora
abbiamo testa pettinante,
mentre passate le cose sì, perché siamo abbastanza particolari, ma secondo me erano anche ok, va bene, va bene, ok, ciao.
Cosa vorrebbe scoprire che è SSD? SSD. È di quelli anche super veloci. E noi quando spostiamo filmati si fa da vicino. Io mi sei stato giù, deve aver portato su un tappetino. Adesso ti arrivano messaggi, ti arrivano mezz'ora dopo. Quando ti scrivevo della fruga arancione, ti è arrivato un'ora dopo.
è arrivato
Ma prima del viventi c'erano gli altri. Che te mi dicevi, ma la spina. Guarda, te mi hai scritto la presa, e ti ho scritto, era la prolunga arancione, vedi? C'era uno del mezzo. Sì, blu. Tra l'altro sono arrivato molto dopo. Quando mi dicevi ma l'ha presa, ancora erano. Sì. Ma anche quando ti ho scritto stringi per favore, facevo così quando arrivavo. Lei ha dei problemi. Perché fino a stanotte ho fatto più della tenda perché se no coscevo. Sì, c'è una performance. Io non si va bene e poi facevo. Ci ha salvato la vita, diciamo. Claudia, ma tu vai adesso? Io vado quando vuoi andare tu. Certo. Vuoi che sei andato per entrare? Qualche minuto di tempo. E pensare che prima di partorire portiamo anche tutti i giorni. Poi l'anno di gravidanza non l'ho messi mai per paura di cascare tutte, ora no, riesco a portarli qualche ora, ma poi mi fanno buonissimo il fiato. E addirittura ci sono dei periodi, io sono un corso di informatica con l'IFT, la comunità europea così. mi sono fatta tutte le caserme della Toscana, per cui in quel caso se non ti metti il terriere tacchi, 12 paracadutisti ti mangiano vivo. No, e in quel caso invece ti serve, cioè se ti vesti così, ti rendono come uno di loro, e invece se ti metti elegante, non ti hanno distanza. Io che mi faccio da tutti, rigorosamente vedrai. Avevo guidatori di blindo centavo. Io come straccio mi faccio attaccare. Era il 2006, era l'anno della guerra del Golfo, se legge.
Sergio che devi fare.
Ma mi porti te? Davide mi ha detto che porta Emi in motorino. Te lo giuro.
Quindi se rimasti io prendevo subito la telecamera e andavo al che qualche ripresa fino alle 5:15 adesso fa. Quindi niente. Io prendo, vado subito lì e la
Ma me l'ha detto, ti porta lui all'uomo, così non stai a fare prezzo a piedi fino alla casa. Io ti dico che siamo a detto là.
Sì, no. Stamani non se ne parla.
Poi tanto lì c'è Marco. C'è Marco, noi si va con una di queste due, lì c'è Marco con la sua amica. E poi c'è il tipo di colonna, che è l'osservatore. E che li per Davide fa. Ci vai te, nemmeno se mi paghi, guarda. Ma quindi io cosa faccio? Io comincio a copiare Mamma e poi mi raggiungo là?
Sì. Lasci tutto così. Sì.
No, un cavalletto sì, ma
No, lo portava Marco. Dice da solo la telecamera. Sempre quando vedi che riesci.
tanto io poi la macchina non qui. Se non mi chiudono dentro il cancello.
Lascia da me e lo fa.
No, la parcheggio la macchina. No, non è un review, è già lì. Io stamattina sono venuta direttamente qui, il fatto che iniziava alle 8:30. Io 20 all'8 ero già.
Però per la cosa di oggi, la cosa di oggi parlare con la pioggia non viene. Penso che Galileo nel discutere del Signore ad esempio della rete cellulare c'è scritto però faccio come però diciamo magari questo giro qua sulle passate di qua non benissimo sì?
Okay, good to be back. And now we have Leonardo Salvi, next speaker, who will tell us something I like very much, general relativity tests and precision measurements, and this belongs to fundamental physics. It's part of the conference. Ok, ti dico quando hai fatto 15 minuti. Poi ce n'hai altri 5 e poi 5 di discussione.
Allora, qui come... Ah, okay. Vediamo. Come si fa a passare la presentazione?
Vista schermo intero.
Ah, sì. Ok,
no, mi
sì. Prova. Ah, vai. So, good afternoon. I am Leonardo Salvi. I work in Guglielmo Tino's group. We do essentially atom interferometry for gravity measurements. And essentially today I would like to talk to you about, let's say, a summary of what we are doing in our group concerning general relativity tests and precision measurements. So, in my presentation, I will start by introducing the atom interferometer, especially for gravity measurements. And I will tell you which are the different technologies that one can use to implement the beam splitters and the mirrors for an atom interferometer. Next, I will move to 4 different activities. One is the classical and quantum test of the weak equivalence principle. The second is the measurement of the Newtonian constant G, which presently can be measured at the level of 100 parts per million, but which is, we have an experiment going towards the 10 parts per million level. Next, I will talk about a special kind of atom interferometer operating on a single photon transition, which is a good candidate for the detection of mid-range frequency gravitational waves. Finally, I will tell you how it is possible, at least in principle, to improve the sensitivity of these devices by using the spin squeezing technology, which already other speakers have already anticipated. So, in an atom interferometer, essentially, we do the same thing we would do with light, but with the roles of matter and light exchanged. We take a matter wave, which is this blue wave here, and we split it, reflect it, and recombine it with laser pulses, which act as beam splitters and mirrors. What we do at the end of this interferometer is essentially we measure the population difference between the two states of this interferometer, and from that we estimate the phase of the interferometer. This phase is given by this expression. Essentially, it is linked to gravity by this conveniently large factor, which is the momentum transferred to the atoms times the squared of the interaction time. So increasing the sensitivity means, from this expression, doing three things: increasing the coherence time, increasing the momentum transfer, and decreasing the noise in the estimation of the phase. So the beam splitters and the mirrors can be implemented in many ways, but the methods that use the interaction of light with matter are essentially these three methods. One is the two-photon Raman transition, where both the momentum and internal state of the atom change. The other one is the Bragg transition, where only the momentum of the atom changes. And finally, there is this single photon transition, which is fundamentally different from all the others, because essentially there is an optical separation between the two states. So let's move to the weak equivalence principle test. So the weak equivalence principle, of course, has a long story, but it has been, let's say, measured at a very high level for this Eötvös ratio, which essentially quantifies the violation for the weak equivalence principle for two particles that have a different internal structure and composition. It can be done for macroscopic masses as well as for atoms, so microscopic masses. With atoms, one can perform either a classical, let's say, a test of the equivalence principle, or a quantum test of the weak equivalence principle. So one, for example, could use two different atoms or two different isotopes to test to see if these two fall at the same rate. Or one could use different internal states. In this case, essentially, what we look at is this fraction, essentially, between the gravitational mass and the inertial mass. So if I have two states and no violation, this matrix would be the identity. If I have some violation of the classical equivalence principle, then these become different from one. If I have a violation of the quantum equivalence principle, then I have the appearance of these two diagonal terms. These two diagonal terms can only be tested with superpositions of internal states. And this is essentially an experiment that was carried out with rubidium atoms in a gradiometer. So basically what one can do here is to measure the difference in the acceleration between two different heights, and essentially record one interference fringe versus the other. The points distribute on an ellipse, which is shown in these figures, and one can essentially compare the acceleration of cloud 1, which is in state 1, with the acceleration of another cloud, which is in a superposition of these two states. So like this one, essentially, we could test the weak equivalence principle classically at the level of 10 to minus 9 and put an upper bound to the non-diagonal term at the level of 10 to minus 8. So another activity, let's say related to this one, is to use a different kind of atom, not the rubidium atom, but the strontium atom, and also in another ERC project which is undergoing in our group, also with cadmium atoms. Basically, these two atoms have the same internal structure. They have, let's say, intercombination lines. And here the interest is to test, let's say, the weak equivalence principle with superpositions of optically separated states. So basically, we are trying to now work on essentially a kind of interferometer which compares the accelerations of one cloud which is just in the ground state and another one which is in the superposition of ground and excited state. Except that here we have an optical separation, so we can in principle test the energy dependence of this violation. This can also be done with another method by looking at the Bloch oscillations in an optical lattice. So the measurement of the Newtonian, so in the second topic I talked to you about the measurement of the Newtonian constant, which is well motivated by the fact that various measurements are scattered around because of many unquantified systematic effects. Most of these experiments were performed with macroscopic masses. And so one interesting test would be to measure big G with atoms. Again, we make a gradiometer. So we measure the difference in the acceleration between two clouds at different heights. And one can modulate the position of these source masses, which act as a source for a gravitational field. And in the far and the close configuration, one can get two ellipses. The difference in the phase of these two ellipses is essentially the signal caused by the masses. This measurement produced a value of G with an uncertainty of essentially 100 parts per million. And what is interesting is that one of the most important limits is the statistical limit. The fact that essentially this interferometer is at the standard quantum limit. Okay, so in another ERC project that is undergoing in our group, whose supervisor is Gabriele Rosi, this experiment is essentially enlarged, which in the previous experiment there was half a ton of tungsten masses. Now we have 4 tons of tungsten masses and a very large apparatus. And according to this proposal, this setup should be compatible with the measurement of big G at the level of 10 parts per million. The third topic I will talk to you about is atom interferometry on a single photon transition. So most of the interferometers I've been talking to you about are performed with multi-photon transitions, either Raman or Bragg transitions. So basically you shine 2 counter-propagating lasers on the atoms. Now, let's now imagine that these 2 interferometers, again in a gradiometer, are separated by a very large distance. What happens is that to ensure that a multi-photon transition happens, the laser pulses must arrive at the atom's position at the same time. Otherwise, the multi-photon transition will not happen. So you can see here that in this scheme with multi-photon transitions, you need to introduce a delay between the times in which the lasers send the pulses. And this delay causes an accumulation of noise. So this interferometer for large scales becomes sensitive to essentially to the laser phase noise. However, if one can do this interferometer with a single photon, instead of 2 photons, essentially one only has the travel time between one interferometer and the other, so the photon does not acquire any extra phase noise from one interferometer to the other. So this scheme with a single photon transition essentially can cancel the noise contribution from the laser. which is why it is interesting for very large-scale gradiometers and for proposals for gravitational wave detectors. So we did in our group a proof of principle of this experiment. Essentially, this is our chamber. We used a green lattice to essentially launch two clouds, which are the gradiometer, and then we shine this light of that goes on this clock transition for the single photon transition. Here, essentially, we detect finally the output of these two interferometers by shining blue light on this transition and recording the fluorescence with a photomultiplier. So the results are that essentially one can implement both a gravimeter, where you just measure gravity, so a single accelerometer, or two accelerometers, so again, a gravity gradiometer. In this experiment, we so essentially saw the importance of the intrinsic laser phase noise in a gravimeter, whereas in the gradiometer, this noise is cancelled to a very high degree. So we could observe essentially that we could reach a null deviation only 5 times larger than the standard quantum limit for the given number of atoms. So we see the correlations between the fringes of the interferometers. Moreover, we essentially established a method to imprint an artificial phase shift into this gradiometer. So this is useful because if the phase shift that one wants to record is very small, this ellipse is essentially a line. And it is very hard to fit and then obtain the phase shift for the gravity measurement. So one can use two clouds and with different velocities, and then have this interferometry laser have two frequency components with a different phase. So this will imprint a phase onto the atoms, which can be tuned arbitrarily. And this is how we record essentially the agreement between the applied phase and the measured phase for relatively short interferometers, but this is, let's say, agrees with our understanding of the gravity gradiometer. Finally, I will talk to you about our experiment regarding the spin squeezing. So spin squeezing is in general useful for all these experiments because, as also Moret Hollande said, all these experiments are finally limited by the fact that one has a limited number of atoms. So this flipping of the coin, which happens when you measure the populations at the output of the interferometer, causes this kind of ball here, which is your uncertainty in the determination of the phase. And it scales as the inverse square root of the number of atoms. If one introduces correlations between the atoms, in principle, one can go down to the Heisenberg limit, where essentially the scaling of the phase uncertainty with respect to atom number can be drastically changed. There are many ways to implement this squeezing. One way which we are considering is measurement-induced spin squeezing. So just to give you an idea of how this works, consider just two atoms, two two-level atoms. What we do here essentially is we do a measurement of the total number of atoms that have spin up and the total number of atoms that have spin down without distinguishing the atoms. So if I get the measurement outcome that one atom is spin up and the other one is spin down, then I must have this state. And this state is actually a metrologically useful state. This method can then be generalized to more atoms. What happens in general?
Okay, 5 minutes left.
Okay. Okay. What happens in general is that if one starts with this initial coherent spin state variance, so this is just the initial standard quantum limit, and then we apply a measurement that does not distinguish the atoms with this uncertainty, then if this uncertainty is smaller than the initial variance, one can have the, let's say, the variance conditioned to this measurement outcome to be smaller in principle than the initial variance. So this method has been implemented, for example, for atomic clocks in rubidium atoms. We are looking for an implementation on atom interferometers, especially on operating on the Bragg transitions. So basically what happens here is that we have these two states which are produced by the Bragg interaction. So this is just the beam splitter I was talking to you about at the beginning of my talk. And then we have to figure out a method to measure the population difference between these two in order to produce the squeezing. So the method that we are looking at is to use a relatively narrow transition, one that can distinguish essentially the Doppler effect between these two states, because these two states have the same internal excitation, but different external excitation. So one would shine a probe laser between these two optical transitions, and then essentially record the phase shift of the transmitted light. This phase shift can be made sensitive to the population difference. Especially this sensitivity is enhanced in an optical cavity, because an optical cavity can, let's say, enhance the information carried per photon. So in this paper, we established that essentially with this method and some more tricks, in principle, one can obtain the same performance as if these were two different electronic states. So essentially, we can make this method equivalent to other methods using spin squeezing for atomic clocks. These are the people I work with. And Long and Gunjan are in my lab. We are working with the spin squeezing experiment. Jonathan and Nicola are working with the cadmium and the strontium. Manan, Jain, Gabriele Rosi are working with the rubidium experiment. Guglielmo Tino is our supervisor. I've been working with Vladan Vuletic at MIT regarding the spin squeezing project. And we did also with the group of Morey and Marilou another proposal for spin squeezing on atom interferometers that essentially can induce an Hamiltonian that is a spin squeezing Hamiltonian. So this Hamiltonian essentially works like this. When this atom passes from the ground state to the excited state, in a Bragg transition, there is the emission of this photon, which can be cached by another atom to excite. And this causes the correlations, which then become this Hamiltonian. So, in conclusion, I told you that we can do tests of the weak equivalence principle and measurements of the Newtonian constant of gravity. Essentially, what's important is that we can do the measurement at this quantum level, so we can test these non-diagonal terms in this matrix. It has been done with a hyperfine transition, so with relatively low energy, and we are looking forward to do it with optical transitions. There is the G measurement towards the 10 ppm level. I told you about our proof of principle experiment for atom interferometry on an optical clock transition, which can, in principle, cancel the laser phase noise contribution in a gradiometer. And finally, I told you how we are planning to implement our spin squeezing experiment for atom interferometers. With this, I finished, and I would like to thank you for your attention.
Okay, very good. Questions? No questions. Oh, good.
So for the single photon case, you were saying, apart from reducing the noise, you were saying the advantage of doing that is that you can monitor how
the effect, if you see it, could depend on energy, meaning it's a much higher energy. Is that what you mean?
Yes. So this is okay. So in principle, it's not useful for the interferometer itself to have a different such a large energy.
Yes.
It can be useful if, for example, you're doing a weak equivalence principle test and you want to make a superposition between optically separated states. So basically, the difference compared to the experiment that has been already done is that you have a bigger separation in the energy, so you can test the energy dependence. There is no real theory about this except for a few conjectures, but and this is probably what motivates this work. Yes, so the optical separation is mainly, I would see it from that point of view. Yes, this is basically what I would say.
Thank you.
Other questions? No, you just. Okay, again.
Sorry, just a clarification. Among one of the very first formula you gave, there were 3 terms. One was the time. The first one was...
So KF is, so basically, H bar KF is the effective momentum transferred to the atoms
by the laser.
in a beam split. Okay.
And then there was G. G is the acceleration.
Acceleration,
And so that's really it, meaning that the phase shift is given by those 3 terms.
Exactly. So basically, KF T² is how sensitive you are. So having it large gives you a larger sensitivity to small g.
Okay.
Yes.
Okay, thank you.
Good. Okay, so thank you again for your talk. Okay, now I think we have our last speaker, who is Enrico Trincherini, and he will talk about black hole ring down as a probe for dark energy. So a lot of black hole ring down today.
Grazie. So thank you for staying until the last talk. Today you saw several styles in physics research, some hard and important experimental results, some nice, what is not this one, but it's not, some more some difficult theoretical computation, like the one done by Giovanni in Axion, the evolution of strings in Axion Cosmology. I will instead play the role of the lazy theorist, so I will use only dimensional analysis mainly, and order of magnitude estimates, and I will ultimately fail, as Riccardo was saying during the coffee break, because in this field there's the cosmological constant problem that is there, whether the cosmological constant is 0 or not. We don't understand why. So this is something that will cast a shadow on all these attempts. Nevertheless, I will try to keep an open-minded point of view, and I will try to see if we can use this process, which has been beautifully described in the previous talk, to detect some new light, massless degree of freedom, even if it's very, very weakly coupled to the standard model. And as we know, there are reasons to look for this type of fields. Maybe they explain why we see dark energy, or maybe dark matter. So Of course, one can have some prejudice about this type of matter. For example, Giovanni was saying that this is beautifully explained and simply explained by the cosmological constant. That's true, but today I want to set aside some theory prejudice and just to look for what we can learn from experiments. So why can we detect light degrees of freedom? Because so I will start from the assumption that there is a dynamical degree of freedom that explains why the universe is accelerating during the expansion. And if this is the case, this means that this field that fills the universe acts like a medium with some homogeneous and isotropic stress tensor, and this breaks spontaneously Lorentz invariance, and so this implies that gravitational perturbation that travels in this medium can propagate with, for example, a speed which is different from the speed of light. It's not necessarily true, but it's a possibility. So this implies that already at the level of the quadratic action or the linear equation of motion, gravity is affected by the microscopic theory of this field. And since we have now a measurement of the speed of gravitational waves, which is the same as the speed of light up to an incredibly high precision, this has implications for the dark energy model. And I would like to see if there's a way to use another, to study the same idea on a different length scale, not the universe, but the length scale typical of black holes, and see if we can learn something about this field in this context. Of course, there's a huge difference between these two cases. In the first, we know that the background, if we assume that is the origin of dark energy is given by an additional field, we know that there is this scalar background which fills the universe. In this case, if there is some background around black holes of the same field, then this will have consequences, and then we can hope to learn something about this dark energy model. But since we have not observed this type of background that implies a deviation from the Schwarzschild metric, in this case, of course, we have to assume that this is the case, okay? And we will see if this is true, what the consequences are. And in particular, as has been discussed before, perhaps the best probe to learn something about this is the last phase of the merger process of the black hole, which is the ring down. Now, there are two possibilities to explain the accelerated expansion of the universe, given some new degrees of freedom, and the possibilities are that this field produces a sizable stress energy tensor, and in this way the geometry responds to this stress energy tensor. The other is that we can still see what we call an accelerated expansion, but this is not given because there's a large stress energy tensor, but because there's some additional field which is coupled to matter in some precise way. So in this second possibility, this is what we usually call modified gravity. The propagation is affected even when there's no matters, when the geometry is flat. So I will mainly consider this case. So assume that there is a large background for the scalar, and this is what sources the accelerated expansion. Now, of course, there can be many models that do this. And my rules are that I would like that the dynamics of this model is robust because of some symmetry. that can be either exact or approximate. And in this way, I'm able to define, at least at low energy, a consistent effective field theory. And the other rule is that I will try to allow for the largest variety of observable signatures, with the hope that maybe one of these will turn out to be observed. So let's start with the simplest thing that we can have, gravity plus the scalar. Then the first assumption is that I will consider a scalar which is shift symmetric. This is simplifies what I'm going to do. It's not really, it's more a technical assumption than a physical one. Then, so for example, these allow for infinitely many interaction that involves derivatives of the field. Now, the other thing that has been done for 10 years now is to include, together with these operators, even include the possibility that there can be other interaction of this field that contains derivatives higher than 1 per field. And of course, operators like these are always there in an effective field theory, but if they are suppressed by the same scale as the one with less derivative, they will be negligible compared to the first one. So the assumption is that instead the scale that suppresses these higher derivative operators is much lower than the one that suppresses operator with less derivatives. So if this is the case, there can be situations in which these are as important as the other ones. And this is possible because there is an approximate accidental symmetry in this Lagrangian, which is the one under shift of the velocity of the field, that protects these operators. So this is the reason why they can be much larger than one would expect. Then, consistently with what I was saying before, I will assume that there's no gravitational coupling of the scalar to standard model fields. Well, these will be generated by gravitational loops and so on, but and the reason is that once we have this type of behavior, which was a necessary ingredient in the second option of the two dark energy versus modified gravity model that I was discussing at the beginning, the reason why this is problematic is because when this, if this can be useful to explain why the behavior of gravitational dynamics is different from the one of GR at very, very large scale, this will translate into an additional force at shorter scale, and this is very, very strongly constrained. So this is why we don't, we try to avoid this possibility. Now, so this is the basic type of theory that I have in mind. So these operators with one derivative, this one with higher derivatives. And since I want to describe the acceleration of the universe, so the stress energy tensor given by this should be of the order of the energy density of the universe today, which is given by this thing here. So this sets what the scale have to be if these type of interaction are responsible for the acceleration of the universe. So in particular, this tells you that the scale lambda 3 is in length scale, so the inverse of lambda 3 is 1,000 kilometers, while lambda 2 is 10 order of magnitude larger. Okay. So this also means that so this theory will become strongly interacting because of this type of interaction at the lowest of the scale, this 1,000 kilometers. Of course, this is just one example of the possible interaction that one can write. They are much more complicated in general. They have this form, and as you see, they are parameterized by a set of functions. The first does not contain higher derivative operators, so it's just a standard Lagrangian for a shift symmetric field, and then there are these three others type of interaction where you have 1, 2, or 3 of these higher derivative terms. The problem with this type of interactions is that you take one, for example, this one, and now this second covariant derivative contains also a piece which is the derivative of the metric perturbation. So this, once is evaluated on the cosmological background, this pi 0, give rise to a correction to the speed of propagation of gravity. And you see here the parametric of this effect. If this operator is order 1 relevant on cosmology, this means that the speed of propagation of gravity is affected by order 1. While we know that this is not true, because we have now this very, very strong bound on the speed of gravity. So this means that either this operator has a very, very small coefficient, or that the UV cutoff of the theory is higher than this 1,000 kilometer scale. So I will take this second possibility in the following. So the first reason is that this will, I mean, if we raise m enough by, for example, 3 orders of magnitude, remember that, so there are 10 orders of magnitude between these two scales. If we set m to be lambda 2, then the theory becomes just a standard shift symmetric theory, so there's no remnant of this approximate symmetry under shift that I was mentioning. That's one possibility, but there's a lot of room to change this scale to be compatible with the limit set by the speed of gravity. So if we raise this by 3 orders of magnitude, that's enough to suppress the effect of this operator and explain why they don't give a large contribution to the speed of gravity. Of course, there's another, perhaps more important reason to raise the scale that is related to a series of results that are completely independent of the application to cosmology, that are simply due to the use of some basic principle of quantum field theory, like Lorentz invariance, properties of scattering amplitudes. This suggests that one cannot separate the scale of these two operators, the one that breaks this symmetry under shift of the derivative and the others, by too much. And so this has been discussed so for the first time in this paper by Riccardo and Alberto and others. So if you just assume some properties for the S matrix, like unitarity and analyticity, this implies dispersion relation for forward scattering amplitudes, and this translates into a bound on this coefficient that tells you that this type of operator must be there. But you can refine this argument and put an actual bound on the size of this term, which tells you that the scale m cannot be too low, and in fact has to be at least 10 to the 5 higher than this 1,000 kilometer scale. Now, of course, if these operators are there, with this scale, they are irrelevant on cosmological length, but they can be relevant at shorter scale, because these are irrelevant operators that are more important at short scale. So the idea is that we can probe them in the case of black holes, so at much shorter scale. So the question is whether we can see their effect in the spectrum of quasi-normal modes. Now, as I was mentioning before, the main difficulty in this case is that there are results that tells you that it's hard to have a non-trivial solution for scalar fields around black hole. And there's one, so there are theorems that explain you why this is difficult, but there's one interesting exception. If you have this type of term, So if the scalar is coupled to this Gauss-Bonnet combination, which is by itself a total derivative, but once you couple to pi, it becomes some local interaction. And of course, the fact that this is a total derivative tells you that the coupling is shift invariant. So once you add this coupling to the theory, black holes can have non-trivial solution for the scalar field. Of course, we don't know what the coupling of this operator is. So what we can say is hopefully how this will affect the spectrum of quasi-normal modes. And this is what we can compute. So sorry, if we consider a black hole, and in the presence of this term, the solution, if you start far away, is given by the equation of motion that is given by the scalar, the kinetic term, and then this in the equation of motion. So you remove this pi, act as a source for the scalar given by r square is the curvature square of the black hole solution. So let's take a Schwarzschild black hole. So this will source a pi that grows going closer to the black hole, and at some point this object will become large. So if I consider a region where these are both much larger than one, then one of the operators in the Lagrangian will be the dominant contribution, depending on the one that are present. Okay, and this is what set the scale for the solution, this pi 0 in a spherically symmetric background around the black hole. Once you know this solution, what you can compute is the kinetic mixing due to this operator, which is the form of this form. So you take one of the r is d square h, so it gives you this dh d pi kinetic mixing. The other r is computed on the background, the Schwarzschild metric. So this kinetic mixing, well, first of all, you have to canonically normalize the scalar, because together with this, the field pi also will get around this background some large correction. So the physical effect is obtained once you canonically normalize the field, so it's given by this dimensionless quantity. And if this, well, this is a naive estimate of how the spectrum of quasi-normal mode should be affected, okay? Because if you mix the gravitational equation that you have in GR, so the linearized equation with another degree of freedom, this scalar, and this mixing is order 1, what you get is an order 1 deviation in the spectrum of quasi-normal mode. Of course, this has to be computed, as we saw in the talk about quasi-normal mode, at the light ring of the black hole, which is more or less at the size of the Schwarzschild radius. Of course, the same coupling that give rise to this mixing and therefore to the modification of the spectrum of quasi-normal mode is also responsible for the emission of a gravitational wave during the in-spiral phase of the merger process. And even if we don't detect this scalar wave emitted, if it is there, this will make the evolution be faster than in the presence of just GR. And so the analysis done so far puts some bound on how large this effect can be, which in terms of this coupling A, which is a dimension of a length square, it has to be smaller than kilometer square. So in the end, this will translate into a bound on how large the deviation in the spectrum of quasi-normal mode can be. And this is the last slide. So this is a table that you should read in this way. So you choose one operator to be the dominant in the regime of scale where these x and z solution are large. That can be, for example, one of the following. And then you can see what the size of the effect on the deviation in the quasi-normal mode should be. This is the upper bound, okay, that is compatible with the in spiral bound on the emission of scalar wave. And you see this is of the order of 10 to minus 3 or maybe slightly larger. Okay, so this means that, as we saw, it's interesting to push this type of analysis down to really per mil level, for example, because there can be some interesting physics in these very small corrections. Okay, of course, as I said, this is just an upper bound, so we don't know what the scale of this operator will be. So the only condition that we can impose is that cannot be too large, because otherwise it will affect, since that is an operator that breaks this accidental symmetry, at some point that will lower the cutoff of the theory too much, and it cannot be too small, but okay, that's not, because its size is set by the quantum corrections, but it's not important. So the conclusion is that, okay, maybe dynamical dark energy is still an interesting possibility, and there's even the possibility that it leaves an imprint in the black hole merger. Of course, this is true if there is some non-trivial solution for the scalar, so these dark energy fields around black holes. So this means that one should be interested in understanding more if this so-called hairy solution exists or not. And the fact that there are no Hairy theorems is not, this is an N, should be an N, is not very restrictive, because there are several ways to avoid this type of theorems, like introducing non-trivial boundary condition, time-dependent solution, one can break the shift symmetry, and so on, or use these type of interactions like the one I was describing. That was just one example, okay, to show that this is really something that can be done. And this is why perhaps it's important to adopt a more theory agnostic approach to study this type of signature. Instead of computing, like many people do, the deviation of the spectrum of quasi-normal mode in a given model, it's perhaps more useful to adopt a different approach, the one that I've been developing with other people like Riccardo Penco, Luca Santoni here, which is to use an effective field theory around the geometry of the black hole to describe the quasi-normal modes. This will be useful to understand what type of behavior in these frequencies is allowed under some very general condition. Of course, all of what I said is about Schwarzschild black hole that are not the one that are really interesting for observations, because we know that black hole that result out of a merger have a spin. So this should be generalized to the case of Kerr black hole.
Okay, I think we
Thank you.
stop here. Thank you very much. Question? Questions? Too complex talk. Okay, or perhaps everybody wants to go to the Piazza dei Miracoli. Okay, so let's thank the speaker again, all the speakers of this afternoon.